I will see some homeomorphism. How many homeomorphisms exist from S4 to Z4, Z4 to S4, Q8 to S4? This type of question, actually this type of question, counting homomorphism, this type of question actually very important for any competitive exam, also for higher study. I have discussed today briefly for geometrically how many homomorphisms exist from a group to any group. Okay, so at first I will highly recommend you, if you don't see my previous video of counting homomorphism, at first see those videos, then you will understand today's video in better way. I have given the links in description box. Please see my description box. I will see one question of group homomorphism. I will say find the number of group homomorphism from Z4 to S4. Just as a review, today I will discuss this part just as a review. At first, see the structure of S4. Here the elements are of order 1 identity. Order 2 elements are 1 2, 1 3, 1 4, 2 3, 2 3, 2 4 and 3 4. And another type of order 2, 1 2 3 4, 1 3 2 4, 1 4 2 3. There are 9 elements of order 2 in S4, and there are also elements of order 3 in S4. The elements are 1 2 3, 1 3 2, 1 3 4, 2 4 3, 3 4 1, 3 1 4, 4 1 2, 4 2 1. And other element of order 4 is 1 2 3 4, 1 4 3 2, 1 3 4 2, 1 2 4 3, 1 4 2 3 and 1 3 2 4. Then how many subgroup exist from F from Z4 to S4? Now we have to find normal subgroup of Z4. The normal subgroup of Z4 of 1 order, 2 order and 4 order, and the normal subgroup are look like of Z4 are look like cyclic subgroup generated by 4 modulo 0, which is actually the cyclic subgroup generated by 0. Cyclic subgroup generated 4 modulo 2, this is actually cyclic subgroup generated by 2, and 4 modulo 4, this is cyclic subgroup generated by 1. This is the normal subgroup of Z4. The group are Z4 modulo the cyclic subgroup generated by 0, this is would be isomorphic to Z4, which is obviously subgroup of S4, because notice here obviously this would be cyclic type subgroup, and in S4 there are 3 subgroup of order Z4 type. How? One subgroup would be generated by 1 2 3 4. This means if we consider a square, a cubes, this would be 1 2 3 4 first. If we square, then this would be 1 2 3 4 type, and then after a cube this would be 1 4 3 2, then identity. Similarly here for this these 2 element has included in this subgroup. So other subgroup would be, if we consider the cyclic subgroup generated by 1 3 4 2, similarly this would be 1 3 4 2. If we square, then this would be 1 3 2 4. and another would be 1 2 4 3 and identity. If we consider this is H1, this is H2, that means similarly I will get H3 also, that because H3 would be constructed by this cyclic subgroup. Therefore there exists in S4 there exists 3 subgroups of order Z4 type. So number of homeomorphism when the quotient group is isomorphic to S4, this would be calculated by automorphism of Z4, and number of 4 order subgroup in S4 is 3, and automorphism of Z4 is actually 5 4 into 3, and 5 4 equal to 2 6. That means there are 6 homeomorphism when the factor group is such type. Third factor group would be Z4 modulo cyclic subgroup generated by 2. Z4 modulo cyclic subgroup generated by 2, and this is isomorphic to Z2. And how many subgroup exist in S4 Z2 type? Notice there are 9 elements of order 2 in S4. 1 2 3 4 5 6 7 8 9, and number of subgroup of order 2, number of subgroup of order 2 in S4 are number of elements of order 2 in S4 divided by phi 2, and this would be 9. And the subgroup would look like, if we consider A is 1 equal to identity 1 2, identity 1 2, then A is 2 would be identity 1 3. Similarly, A is 4 would be identity 1 4. A is 5 similarly, A is 3. So then I will get A is 4, A is 5, A is 6. A is 6 would be identity 3 4. Similarly, I will get A is 2, A is 3, A is 4, A is 5, A is 6. Then A is 7 would be identity 1 2 3 4. Identity 1 2 3 4. Similarly, I will get this is A is 7, A is 8 and A is 9. So there are A is 8 and A is 9. There are 9 subgroup of order 2 in S4. 9 subgroup. That means automorphism of Z2 times 9, and automorphism of Z2 equal to 1. That means there are 9 homomorphism when the quotient group is 2. This is the quotient group, cyclic subgroup 2, cyclic subgroup generated by 2, who is mapped to only identity, and another 1 plus square root 1 plus cyclic subgroup generated by 2. This can map to either 1 2 or 1 3 or 1 4 or 2 3 or 2 4 or 3 4 or 1 2 3 4 1 3 T 4 or 1 4 2 3. That means there are 9 ways to map 1 plus square root of 2 in this element. So there exists 9 homomorphism. I hope my all viewers have understood this picture, how there are 9 homomorphism exist when the quotient group is isomorphic to Z2. Okay, well, the factor group would be when the cyclic subgroup generated by one Z4 factor group would be, another factor group would be Z4 modulo cyclic subgroup generated by 1. This is actually isomorphic to trivial subgroup. This type of homeomorphism, actually this is the trivial homomorphism. All elements map to actually the identity. That means there are number of homeomorphism 6 plus 9 plus 1, and this is equal to 16. Therefore, number of homeomorphism from Z4 to S4 is 16. I hope my all viewers have understood this question. Okay? Oh well. I will see one question which had come in CSIR NET exam. G equal to S3, where S3 is a non-abelian group. Permutation group of three symbol, then G is isomorphic to a subgroup of cyclic group. Is it true? Since the group is non-abelian, so it cannot be isomorphic to a subgroup of cyclic group. So option 1 is wrong. Next I will see at first option 3. G is the product of cyclic group. Is it possible? When the group is abelian, then we can write G as a product of cyclic group. We all of us know. But here the group is non-abelian. So option 3 also wrong. Option 2. There exists a cyclic group A's such that G maps homeomorphically onto the A's. Is it true? Obviously. Consider one mapping S3 to plus minus 1, which is isomorphic to Z2. Then mapping is such type phi sigma equal to plus 1 when even permutation. And phi sigma equal to minus 1 when odd permutation. Okay? Then when the even permutation, this is actually nothing but A3. Then by the quotient rules, S3 modulo A3 is isomorphic to actually Z2, and Z2 is a cyclic group. So, and this is homeomorphically on the cyclic group Z2. So there exists a cyclic group A's such that G map homeomorphically onto A's. This is right option. And option 4, there exists a non-trivial group homeomorphism from G to additive group Q. Is it true? Here S3 to additive group Q. This type of non-trivial group homeomorphism possible? Notice, we all of us know by homeomorphism, here the kernel of S3 are one identity, then A3 and S3. By factor rules, S3 modulo identity is isomorphic to S3. S3 modulo A3 is isomorphic to Z2, and S3 modulo S3 is isomorphic to identity trivial. In Q plus there exists no subgroup. This type in Q plus there is no subgroup of S3 type. So this type of homomorphism cannot possible. In Q plus only finite subgroup is identity. Another subgroup are all infinite order. So these type of subgroup in Q plus not possible. So this type of non-trivial homomorphism here cannot possible, and this is the trivial homomorphism. This is possible, but here the question, the non-trivial group homomorphism, this is wrong, because in Q plus there are only finite subgroup is identity, other subgroup are whole infinite order. So option 4 also wrong option. I hope my all viewers have understood this question. Okay. OL. Say number of counting homomorphism Q8 to S4. Few minutes ago I had seen number of counting homomorphism from Z4 to S4. Now I will say number of counting homomorphism Q8 to S4. I hope my all viewers can easily solve this question, because few minutes ago I have solved this type of question. We all of us know every subgroup of Q8 is normal, since the group Q8 is abelian group. So kernel is car phi equal to identity plus minus 1 I j k, and these are isomorphic to Z4. We all of us know. So the quotient group are, the factor group are Q8 modulo identity, which is isomorphic to Q8. In S4 there exists no subgroup of Q8 type. There exists subgroup of order 8 in S4 default type. So this is not subgroup of S4. Then next Q8 modulo plus minus 1, and Q8 modulo plus minus 1, this is either this would be 4 either isomorphic to Z4 or this is isomorphic to K4. But notice, we all of us know, if G modulo ZG is cyclic, that implies G is abelian. But we all of us know Q8 is non-abelian group. So G mod ZG is cyclic, this is not possible. So Z4 cannot possible. Only possibility is K4. And we all of us know in S4 there exists subgroup in K4 type. So this type of homomorphism is possible. Homomorphism would be such type when car phi equal to plus minus 1, then the homomorphism would be car phi belong to plus minus 1, then other coset would be plus minus 1 times I plus minus 1 times j plus minus 1 times k. And here in Q8 the subgroup of K4 type is identity 1, 2, 3, 4, 1, 2, 3, 4. This is one possibility. Other possibility is identity 1, 3, 2, 4, 1, 3, 2, 4. Other possibility is identity 1, 4, 2, 3, 1, 4, 2, 3. Identity, other possibility identity 1, 2, 3, 4, 1, 3, 2, 4, and other is 1, 4, 2, 3. We all of us know in S4 there are 4 subgroup of K4 type. Because few minutes ago I have seen the structure of S4. So plus minus 1 always map to identity, and plus minus I map to either 1, 2 or 1, 3, 4 or 1, 2, 3, 4. That means there are 3 choice for plus minus 1. Similarly, for plus minus j there are 2 choice, and plus minus a there are 1 choice. Sorry. That means for this there are 6 choice. Similarly for this there are 6 choice. Similarly for this. Similarly for this. That means when curve phi equal to plus minus 1, the number of homeomorphism, since there are 6 choice and in S4 there are 4 subgroup of K4 types, that means 4 times 6, 24. That means when curve phi equal to plus minus 1, so number of homeomorphism, then the number of homeomorphism is 24 times. Okay. Next I will see when kernel is I and curve phi equal to 1, I, then Q8 modulo cyclic subgroup generated by I would be isomorphic to Z2. Then the homeomorphism would be such type. Few minutes ago I had seen in S4 there are 9 subgroup of order 2 type. Now I will see how possible this is. Curve phi equal to cyclic subgroup generated by I, who is isomorphic to Z4. Then the quotient group would be such type. This is cyclic subgroup generated by I, and this is cyclic subgroup generated by I times J. Here the subgroup of order 2 in S4 is such type. Here identity 1, 2, identity 1, 3, identity 1, 4, identity 2, 3, identity 2, 4, identity 3, 4, identity 1, 2, 3, 4, identity 1, 3, 2, 4, and another identity 1, 4, 2, 3. Always I map to identity, then it can map to here. Similarly it map to here. Similarly it map to here. 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 Sorry. It map to here. Similarly it map to here. It can be mapped to here. It can be mapped to here. It can be mapped to here. That means when the curve phi equal to cyclic subgroup generated by I, there is exactly 9 homomorphism. Similarly, I will get 9 homomorphism for cyclic subgroup generated by J, cyclic subgroup generated by K. That means here 9 homomorphism, here 9 homomorphism. That means total number of homomorphism, here I have got 24 homomorphism for plus minus I. That means 24 plus 9 plus 9 plus 9. And when normal subgroup is Q8, then Q8 modulo Q8, this is actually identity, and this homomorphism is actually trivial homomorphism. That means total 52 homomorphism possible from F from Q8 to S4. Is there exist any injective homomorphism? When kernel phi is identity, then injective homomorphism possible. But here for kernel phi identity there exists no homomorphism. So no 1-1 homomorphism. Similarly, no onto homomorphism. Because when image is similar to isomorphic to S4, then this homomorphism would be onto. There exists no onto homomorphism. There exists 52 homomorphism exists. And if question about how many non-trivial homomorphism would be or exist, this would be 51. Today I will stop here. And if you have any queries about my channel, please do comments in comments box. Okay? See you soon. Stay safe and stay positive always. Thank you so much.